The various definitions of convergence that we have given are all quite involved. Now that we have made the effort to master these definitions, there is no necessity to be extremely verbose when writing down proofs or studying convergence or divergence of various sequences. It is very useful both from the perspective of elegance as well as clarity to use language in our aid to communicate in an effective manner. So, let me introduce a few definitions that will make it easy to talk about convergence and divergence in a precise manner, but at the same time not too wordy. Definition. Definition. This is the definition of property holding for sufficiently large n. So this is going to define what it means for something to be true for sufficiently large n. Let P of n be a property defined on the natural numbers. We say P of n is true for sufficiently large n if we can find capital N in n such that P of n is true if n is greater than n. Okay? So what this definition is saying is that the property n should be true for sufficiently large n means after some natural number, for sufficiently large natural numbers or for suitably large natural numbers, P of n is true. And that is captured by saying that there is some point n beyond which this is true. Now, notice this funny thing that property holding for sufficiently large n does not specify how large we need to go. It could be the case that we may have to go n greater than 10 million or 10 trillion or 10 trillion million. It could be very, very large. That does not matter. Okay? So, we will usually say that P of n is true for sufficiently large n. We will also use certain synonyms just for variety to spice up life. We'll say P of n is true for suitably large n, or P of n is true eventually, or even a fancier one which is also the same but it's useful in many other contexts as well. P of n is true for all but finitely many n. These are various versions, various phrases that we shall use to describe the same thing. So now that we have this additional terminology, the definition of convergence becomes rather easy, which I state as a proposition and I leave it to you as an exercise because it's just a matter of unwinding the definitions. The sequence xn converges to x if and only if for each epsilon greater than 0, xn is an element of bx epsilon for sufficiently large n. This is just a reformulation, and as you can see, we have gained a great economy in our expression. Okay, so now let me make some more remarks. Note the role of epsilon in each of the definitions that I have stated. Okay, there are several, I think 4 by my count. The role of epsilon is that it is a fixed quantity but otherwise arbitrary. Okay, and our goal is to show, usually when you are showing convergence, goal is to show that some particular algebraic expression can be made less than this epsilon. This algebraic expression is mod xn minus x naught. We have to somehow make it less than epsilon. Of course, we have flexibility in this small n. We can choose this small n by our desire to, we can make it really large. But at the end of the day, we have to show that this expression is made, can be made less than epsilon. In other words, the role of epsilon is to make mathematically precise the notion that a particular algebraic expression that involves a variable n can be made arbitrarily small or as small as we desire by increasing n. So the role of epsilon is to make mathematically precise the notion that some algebraic expression involving n can be made arbitrarily small. That is exactly what, or as small as we desire. That is the role of epsilon. Let me be precise, as small as we desire by making n large, right? And how do we achieve this? You will see in the module on examples that we achieve it by manipulating the expression as much as possible. Sometimes it's easy algebraic manipulations, sometimes it's messy algebraic manipulations, and often what will happen is, once you do all the manipulations to show that mod xn minus x naught is less than epsilon, you end up with something like mod xn minus x naught is less than k epsilon, where k in R is a fixed constant. The fixed constant independent of epsilon. In other words, instead of getting mod xn minus x naught is less than epsilon, we may end up with getting mod xn minus x naught is less than 3 epsilon. Now, of course, if you have been following what I'm saying, this shouldn't really matter, because the role of epsilon is to say that mod xn minus x naught can be made arbitrarily small. If it can be made 3 times arbitrarily small, 3 times arbitrarily small is still arbitrarily small. This is of no consequence, and we illustrate this with the following lemma, which makes precise what I'm trying to say. Lemma. This is called the K epsilon principle. The K epsilon principle. Let E of n be an algebraic expression that involves n. Suppose if you are not very satisfied with this with this particular phrase, let E of n be an algebraic expression that involves n, you can just say E is a function from the natural numbers to the real numbers. Okay, suppose E of n is less than k epsilon whenever n is sufficiently large. So this is an opportunity for you to see our new enhanced vocabulary in action. When n is sufficiently large, then E of n can be made arbitrarily small for sufficiently large n. What do I mean by E of n can be made arbitrarily small for sufficiently large n? That you will see in the proof, but you should have guessed what this means from the discussion that we had above. Proof. what we have is that E of n can be made less than k epsilon whenever n is sufficiently large. So fix epsilon greater than 0 and set epsilon 1 to be epsilon 1. Just one moment. One catch that I forgot to mention that involves, and suppose E of n less than k epsilon where k is greater than 0. This is crucial. Okay. Fix epsilon greater than 0 and set epsilon 1 by definition to be epsilon by capital K. Okay. Then for suitably large n, E of n is less than k epsilon 1. Why is this the case? Well, that's what is the definition of we have just set in the definition that E of n let me rephrase that. In the hypothesis that E of n is less than k epsilon whenever n is sufficiently large, that epsilon could be any number whatsoever. Okay. What we have done is we have chosen that epsilon to be epsilon 1. Okay. So to make sure that there is no confusion whatsoever, suppose for each epsilon greater than 0, E of n is less than k epsilon, k greater than 0 whenever n is sufficiently large. Suppose you can do that for each epsilon. In particular, you can do it for the choice of epsilon to be epsilon 1. Okay. So E of n can be made less than k epsilon 1 whenever n is suitably large. But this is just epsilon. Right? This is just epsilon. What this is saying in the end is that E of n can be made less than epsilon for suitably large n. This just says that E of n can be made arbitrarily small. The definition of can be made arbitrarily small is as you increase n, it is possible to make E of n less than epsilon. So this proves the lemma. So this lemma I will not explicitly invoke in the proofs. If it gets too messy in the proofs, in some proof of convergence, or I will just leave the expression on the right hand side as some constant time epsilon and just say that we are done. I will not explicitly invoke this particular lemma. This is a course on real analysis, and you have just watched the module entitled A Descriptive Language for Convergence.